Since they're both an extremely good model for describing how to do various many-body quantum mechanic calculations, and because they're the kinds of things that explain nearly all the phenomena we see, let's talk about atom-light interactions. And since we already know how to deal with atoms quantum mechanically, we now need to know how to deal with light quantum mechanically. There's two ways of going about this. The first is you can start with Maxwell's equations and try and quantize them, and that's probably the more common method of doing quantum field theory. But the other way of going is by thinking about what a photon must be and then just using many-body quantum mechanics version of lots of photons stuck together. So what do we know about photons? What do we know about light? So we know that the electric and magnetic fields are oscillating in light, and we know that they're oscillating at right angles to the direction of motion. And so an eigenstate is going to have a particular k vector, which defines its direction of motion. And we know the electric and magnetic fields are going to be oscillating transverse to that. So of course we have choices of polarization as well. So in this case we have a vertical polarization and we might have a horizontal polarization as well. So we always have a choice of two, and so we'll have not just an index for k, we'll also have a lambda index, which tells us which polarization we have, and lambda can be one of two states. And so with that lambda, which is two-valued, and a k, we have a complete parameterization of all the possible eigenstates of light. So any electromagnetic field will be a superposition of these kinds of plane waves with these polarizations, and that means that our photons live in a Hilbert space that has a lambda and a k. And the energy of a photon doesn't depend on the polarization at all, it just depends on the k. And so we know the Hamiltonian for a single photon, where this omega k is just, of course, c times the mod of k. And that means we know the many-body Hamiltonian. When you quantize light the other way by taking electromagnetism and quantizing that classical field, you end up with the same Hamiltonian apart from an infinite constant added, because you tend to get that Hamiltonian instead. So you get the normal harmonic oscillator Hamiltonian for each mode. That gives us an infinite offset because we've got an infinite number of these modes, and that basically doesn't affect anything. Even though it's infinite, it's still constant. So when you work out the dynamics of anything, it never changes the dynamics of anything. So we'll often just leave without that. The only time it's worth considering those constants is if you are dealing with some kind of strongly restricted version of electromagnetism. For example, you might have strong boundary conditions induced by a mirror. And in that case, re-quantizing the field for your reduced dimensionality can actually give you simpler calculations, because you find that as you change the distance between those mirrors, you change the number of those extra modes that you're allowing, and so that 0-point energy can actually have an effect and cause a force on the mirrors. That's called the Casimir-Poulter force. But it is, of course, entirely possible to do that with all the modes available, and strongly considering those mirrors rather than as boundary conditions for a reduced theory, but as actual sources and sinks, charges that interact with the photons. And if you do that with sufficient detail, you of course get the same answers. In the absence of photon-photon interactions, that's our complete theory for light. We've got our Hamiltonian, we know exactly how everything evolves. The dynamics there is trivial, of course. We've deliberately calculated what it's going to look like for its eigenstates, so all they do is rotate in phase. In order to relate how light interacts with anything else, however, we're going to need to know some observables. Particularly, we're going to need to know the electric and magnetic fields, which we can get from the vector potential, which is now not going to be a classical field, but a field operator, indeed an observable, but still vector valued, so it's still got three values. And we'll also need to know the electric field operator. So these are now observables. Now we know that we can build any operator out of creation and annihilation operators. It turns out that these observables are simply superpositions of creations and annihilation operators, albeit very large superpositions. They're vector valued, so we have our coefficients now are vector value coefficients. So we have an x, y, and z, for example, coefficient here, because we really have three operators. So this vector value operator is really an ex, an ey, and an ez field. And we know that these things are plane waves, and they have a particular direction which is defined by the polarization. Now, light only affects charges, and atoms are neutral. So does light in fact interact with atoms at all? And if so, what's the dominant interaction between an atom and light?